I collected from drilling. Okay, so remember the diffusion coefficient is measured using a core somewhere else. These data points are drilled into the concrete again somewhere else. So there will be variability clearly. You shouldn't expect exact. But give or take, it looks like the model is okay for the prediction. Okay, I'm assuming the threshold to be either 1 or 0.7. I have the flexibility. Okay, and this is wrong. The average cover depth should be here, 35. So if the cover depth was here, do you think the corrosion would have started? This is your threshold. This is where your cover is. So your chloride concentration exceeded the threshold at the point where the cover depth is, which means mathematically speaking, corrosion should have started. Okay. Even non-mathematically speaking, corrosion is highly likely to start. That's given. 7 years later. Yes. It's not a bad concrete. It has good binder content. It's reasonably good water cement ratio. Diffusion coefficient is low, not extremely low, but it's low. It's the exposure. This is Atlantic Ocean for you. Okay. And obviously, you've no idea how differently the contractor put information between that and this. Okay. I have no reason to not believe the contractor because I have a performance measure here. So I have every reason to believe that they've done what they've told to do. But now I can question whether the standards were sufficient. Well, the answer is before you, it wasn't sufficient anyway. But that's not my focus here. I'm trying to relate that back to a point in my grid. And as happened, it's that point where I measured the concrete dust. Okay? And it's very close to that where I took the core to do the testing. Okay? Okay. So, reference service life in this case, if I move the I don't know what happened here, but if I move the average cover depth to be 50, but I don't know if 50 was what they prescribed and 35 is what they achieved. I'm not sure what happened in between. If the average cover depth was to be 50, then I get 12 years before corrosion starts. That is your reference life. And then the question is, how can I relate that reference to the rest of the grid? So I got reference to be 12 and I got the cover depth. I know the cover depth. I'm going to assume this based on 1 or 2 measurements that I've done and based on literature. I've tested it and I'm going to assume that as well. Okay? I'm going to use a constant threshold, so that's why I'm not considering that. That is my reference location where I measured 12. Every other value, therefore that remains 1. Every other value is with reference to that point. Okay? So if at that point the cover was full 35 or 50, then that's 1. And everything else, if it's above 1, means I have better cover than that point. Okay? You can see, unfortunately, the cover is lower where it should be higher. Okay? And there are good points and bad points. Okay? The greater cover depth means obviously the cage is flexed inwards. And you can see there's a lot more positive things. And I chose that deliberately because that's the lowest cover point. Okay? You can have 1 or more reference if you wish. The next thing is I looked at, I can't measure diffusivity all over the stuff. It will destroy the whole thing. So I used electrical, the 4-pin Werner 4 probe. So I used that on that location before I took the core. And then I used the same everywhere and divided every value with that because everything is in reference to that. Okay? So larger resistivity means it's better quality concrete, it's much better quality concrete. Lower than this means it'll be worse than that. Okay? And you multiply those two factors. If you have more factors, you can multiply those. And the 12 that you had measured somewhere here, which is 12, will then become the grid. So 12 multiplied by the factors. So you can see over here, you have better service life. I mean, the corrosion is unlikely to initiate here. Corrosion is more or less likely to initiate on this side of the structure. So this is my prediction, okay? It's mathematical. What I have on top of it, I have half cells. So I can put it back into half cell and see, is that what I'm getting? Or is half cell telling me a different story? Okay? And if you look at it, the top part of it where the service life is reasonably good, service life is low in these regions, okay? The blue regions. And that's moderate half cell. And extremely low half cells are found here, where the dark patches are. And the pure red is good. So my reference location is a dark one. And the next to it is a better location. And these green means it's reasonably good location. Here where you got extremely high service life, I can see the values are dark to not dark, which means there's highly likely it can corrode in that region. It might have more chlorides in that region, but because it has a larger cover depth, it's unlikely to corrode there. The lower cover depth here means it's more likely to corrode here, and the resistivity was low here as well. So this way you can combine all the information together. You can try the technique. There are loopholes in the theory, and it's not going to be an exact science, because you will have errors in the measurements. So if you want to take it further, please feel free to. There was a published article, so I can give you the article if you wish. By the way, you can download all research articles from Queen's University through qub.ac.uk/research. Let me write. Let's see if it will work first. Anyways. We're slow, but we're working. Okay. So just QUB for Queen's University Belfast. Indicates academic institution.uk/research. So you will have a search option below, and either you can search for a name or a type of paper. And most of the papers are available free. It will work someday. And as part of our funding requirement, we now publish most of our work online, free, because that means more people will get access to it, and that's the whole idea of best practice. Publication is best practice. We had that talk. Don't use it, then what's the point? Wasting time to publish it. I don't know what's happening, but anyway, it'll happen someday. The internet seems to be a bit slow. Okay. Yeah, we're okay. You know the earlier picture, there was a girl with headphones, had a virtual environment, we're investing quite heavily for teaching as well as for research, because imagine you can see all of this before you. It'll help you to take better decisions. Okay, so we can take all the information, we can filter it down, and then we can put it back before you. So you can then decide what's good or what's bad. So if you go into, so the names appear, and the reason my colleague Sonabi appears is because we've jointly authored paper, and that's probably why it's coming up. And then within that they will list out all the papers. While that is ongoing, any questions on that? Approach is free. You can try it on anything that you wish. This is a good standard to refer to. There's several parts, or 10 parts to it. What I'm referring as service life is one part of it, 5 I think, the middle part. So it'll be 5. Each of that will go into, for example, you'll see that later, but some of them will go into life cycle assessment, life cycle costing, service life estimation, which is what this is, data, and all of that. Okay. So it's a good standard to refer to. There's example, ISO standards are quite nice. They put examples in there, unlike the other standards, which are very dry. Anyway, it doesn't want to transfer anything. If it comes up, I'll show you. So, where do we go next? Okay. Everybody will tell about 100 things. You can get an idea of the publications as well as the projects, the different projects we do, and the different activities that we do. So this will be an activity soon, once I go back and get time to enter everything. Okay. Where are we? Dear God. Okay, so for the mathematical part of the work, knowing the theory is good, okay, but to take decisions like what we saw earlier, we need to have the mathematics behind us. So for a mathematical part of it, I'm going to use a model called Duracrete. Has anybody heard of Duracrete before? Duracrete is a product of a European funded project. Okay. You can download Duracrete. You can't download the model, but you can download the booklet, which tells you about the model. It's I forgot. Okay. So it's a European Union project called EDU. Then if you use these keywords and Duracrete, you should be able to get the PDF copy of that file. Try it, and if you can't find it, let me know. Within that, the appendix is the most important part. One of the appendixes is on carbonation, one is on chlorides. I don't know what the other things are. I haven't read it. It's a really big document. But along with that, it will also give you the factors. It's using a factor type style, but not necessarily. So we're going to look at the two equations. When you look for Duracrete, you will also get a publication by a guy called Andreas Lindwall. That's what this is based on. Andreas made it a bit more easier to this is your carbonation modeling. Okay. So according to this equation, the depth to which the concrete will carbonate, XC, is related to, I'm happy to share this folder, this PowerPoint, okay? I know I have to send you the Word document for the thing as well, but I'll send this in. The depth of carbonation XC is related to the square root of diffusion coefficient. You know that carbon dioxide is a diffusion mechanism. Surface concentration of carbon dioxide, binding capacity. So that's why I was saying it's a transport reaction mechanism. And then a function of time. Okay. This T0 by T0 raised to n represents the rate at which the diffusion coefficient will change as the concrete hydrates. Okay. So everything here has a function, has a purpose. K1 and K2 represents the environment and the curing. Okay. So, model. Can you put that into an Excel file? Yeah. That's it. Put that in an Excel file. You should have two columns. One is for XC, which is your output column, and one of the variables should be your T, time. So that means you can get time against depth of penetration in the two axes. You will need to know what K1 and K2 and A and D and CS are, obviously, and that's where the trick is. In service life modeling, it's easier to do mathematical expressions, not really complex, but defining those variables are a tough job, for which you may have to read or develop your own factors. But I'll take you through, so similar to that, there's a chloride model. We'll do that later. Okay, just to get you started and everybody in the same platform so I can help you with comparison. Use these functions, these variables. So K1 is